So as mathematicians began solving problems, they began to wish for a number that actually didn't exist. They needed to invent a number to help them solve problems. And just like your childhood imaginary friend, in come imaginary numbers to save the day. So let's take a look at the first equation. We have x squared is equal to 1. Now we know that there are two solutions for this. X could be -1, -1 squared is 1, and x could also be 1. 1 squared is also 1. But if we look at this problem right here, x squared is equal to -1, we can't find a solution because a negative times a negative is going to give you a positive, and a positive times a positive is going to give you a positive as well. So we have nothing that will answer to this solution. In step imaginary numbers. So mathematicians, just like all the other numbers, defined I squared as equaling -1. They chose that definition, and that helped them solve all kinds of problems. So if I squared is equal to -1, I is equal to the square root of -1. So let's look at how we can solve some problems using our imaginary numbers. If, for example, we have x squared is equal to -9, we can solve that by taking the square root of both sides. So we have x equals plus and minus the square root of -9. Now here we have our definition where I squared is equal to -1. So instead of -9, we can call that 9 times I squared. Remember, I squared is -1, so that would give you a -9 in there. And now we can take the square root. So if we take the square root of 9, we get 3. Take the square root of I squared, and we get I. So we have x. We have a solution here using our imaginary numbers. X is equal to plus 3i and minus 3i. Let's take a look at another example. We have x squared equals -16, and we're going to solve for x. So we take the square root of both sides, and we get x is equal to plus and minus the square root of -16. And instead of -16, we're going to use our definition right here of I squared, and we're going to write that as the square root of 16i squared. Then take the square root. We have x is equal to plus 4i and minus 4i. So let's look at something a little more complicated. We have x squared equals -7. Now we know that 7 is not a perfect square, so we're going to do the same sort of thing. We're going to say x is equal to plus or minus the square root of -7. We're going to replace that -1 with an I squared, and then we're going to take the square root. Now instead of doing anything with this 7, it's just sitting there. So it's just plus or minus I times the square root of 7, or we could write it as the square root of 7i. I like to write the I over here just because then I know it's not under the radical sign. So now if we have a solution, let's say we've got a function here. We have y equals x squared plus 4. We know this is a parabola, and it's opening up, and its y-intercept is at 4. Now it's asking us to find the roots or the zeros. Now when we look at this, we don't see any zeros. It's not crossing this x-axis at all. But that's because this coordinate system is real numbers. It doesn't have any imaginary numbers. So if we were going to solve this, we could set it equal to 0. And we have 0 equals x squared plus 4, subtract a 4 from both sides, and we have -4 equals x squared. And that looks a lot like the problems we were solving before. So we take the square root of both sides, we have plus and minus the square root of -4 is equal to x. And instead of -4, we're going to write that -1 as an I squared, take the square root, and we have x is equal to plus 2i and minus 2i. Not showing up on this, we will figure out how to graph imaginary numbers a little bit later. Let's look at some powers of I. So if we just look at I, we know I is the square root of -1. Now if we wanted to know what I squared is, we have our definition, I squared is equal to -1, but we can use I to figure that out. Square root of -1 times square root of -1 is -1. Now let's look at I cubed. We can look at I cubed as I squared times I. We could also look at it as I times I times I. But that's equal to -1 times the square root of -1, which gives us a negative square root of -1. Now let's look at I to the 4th power. So that's equal to I squared times I squared. Now I could write that a different way if I wanted to. I could write that as I cubed times I. It doesn't matter. You're going to end up with the same answer here. So I squared is -1 and I squared is -1. -1 times -1, we get a +1. Okay, so we've gone through all of this. Let's look at I to the fourth. And again, I wrote it as I to the fifth, I wrote it as I to the fourth times I. You could have written that as I to the third times I squared. It doesn't matter as long as you have the correct number of i's. So that's 1 times the square root of -1, which gives us the square root of -1. That's right back to where we came from. I to the sixth, I wrote it as I times I to the fifth. Again, you could write it any way you want. That's the square root of -1 times the square root of -1, which we know is -1. I to the seventh, we have I to the sixth times I. -1 times the square root of -1, we get the negative square root of -1. I to the eighth, I wrote as I to the fourth times I to the fourth. I really like I to the fourth because it is a -1. Oops, I did that wrong. I to the fourth is not a -1, it is a 1. That's why I like I to the fourth. So I to the fourth times I to the fourth is 1 times 1, which is equal to 1. So I to the fourth is 1 right here. So then I wrote them kind of down this column right here so you could look and see if you could come up with any patterns. You can use these to find higher powers, and we'll do that a little bit later. So now let's talk a little bit about complex numbers. Now, complex numbers actually include both of our imaginary numbers and include a real part. So it combines a real number and an imaginary number. So I have a plus bi right here, and the a is the real part and the b is the imaginary part. Now right here I have some notation. A and b are elements in the real numbers. So that R, remember, means real number system. So I know it's in the real numbers. A and b both have to be real numbers. They can't be imaginary numbers. And so I have an example right here of a complex number. Now a complex number is kind of funny. Complex doesn't mean super hard in this case. It really means parts and pieces, like an apartment complex. And so it has two pieces to it. It's got that real and imaginary part. This is the whole number. This is a whole number right here. It's got a plus or a minus sign in it. So it's not like the numbers we're used to, but it's the whole number. It has to have that connection, that complex part. So we have 7 plus 3i. 7 is my real part, 3i is my imaginary part, and that's a number. That's a complex number. I also have 0 plus 3i. If we could look at that as well, we can have this real part be 0, and then we only have an imaginary part. We can do the same thing with the imaginary part. So 7 plus 0i is just equal to 7. So we can actually write all of our real numbers as a complex number. So that gives us a bigger picture of our number system. Let's move that up here. Okay, so our complex numbers include all of our real numbers and our imaginary numbers. We can write all of them as a complex number. We can just kind of get rid of the real part by putting a 0 in front of it. We get imaginary numbers. We can put a 0 in front of the imaginary part and we'll get a real number. So this is kind of the bigger picture of our number system. Okay, so the question is really, do imaginary numbers really exist? Well, they were invented by mathematicians, but so were every other number symbol that we have. All the real numbers, they're not threes just sitting around in nature. We came up with a name for those numbers, and the same thing is true with imaginary numbers. And the more we learn about them, the more we figure out how important they are in solving equations. So they connect all kinds of crazy equations. They're really important in data analysis. We couldn't really have electrical engineering without them. And they estimate some really hairy equations that we have and functions that we have. So if they look they're really difficult to approximate, we can use imaginary numbers to help us with this. So I would say imaginary numbers exist like any other imaginary numbers. They are really not your imaginary math friend.